Over the last few lectures of this series, we have been describing the issue of scattering in the quantum mechanical context. Let me remind you that in a typical scattering process, particles start out essentially free. There's a bunch of particles which are very far apart from each other. They somehow come together and then they interact. And when you detect them, you do that also in remote future. That is a long time after the interaction. And at that point also they are essentially free. Now the fact that these particles are non-interacting in the remote past and in the remote future has very important consequences, especially about the way in which these particle states transform under, say, the Poincare transformations. Basically, when you have a bunch of interacting particles, specifying particle labels precisely, especially with the view of describing how these particle states would transform under a Poincare transformation, is really not something you can do. The interactions essentially prevent particles from having their individual identities. However, the fact that the particles are essentially free in the remote past and the remote future allow us to define what are called in and out states. These are denoted respectively by a plus or a minus sign on top of the state symbol. So psi alpha plus would be an in state with particle labels alpha, and psi alpha minus would be the corresponding out state with the same particle labels. The way in which we define these states is the following. You say psi alpha plus will be found to have particles described by the label alpha if observations are made at times t going to minus infinity. Similarly, psi minus will be found to have free particles described by the label alpha again, but this time if you were to make the observations at t goes to plus infinity. Note that the states that we are using are states in the Heisenberg picture. They do not really evolve in time. This is why we do not say that psi alpha plus was the state with particle labels alpha in the remote past, simply because it is the same state at all times. Similarly, we do not make such a statement about psi alpha minus either. Note that in the Heisenberg picture, the observables that you use to describe a system evolve in time. So measurements made at different times, even on the same state, will of course have different results. And that is exactly what this definition is referring to in this case. Using this notion of in and out states, we can say that if we prepare a bunch of particles with labels denoted by alpha in the remote past, and after they interact, detect them in the remote future to have particle labels beta, then what we are really doing is trying to detect whether a system which is in the state psi alpha plus can be observed in the state psi beta minus. And the probability amplitude for doing that plays a central role in this theory and is called the S-matrix element. The beta alpha element of the S-matrix is given by the overlap between the states psi beta minus and psi alpha plus. Of course, the modular square of this quantity is the probability that a bunch of particles prepared in the state psi alpha plus will also be observed to be in the state psi beta minus. A related and very important concept is that of the S operator. The S operator is an operator whose matrix elements between free particle states phi beta and phi alpha is the same as S beta alpha. Note that these states here, phi beta and phi alpha, are free particle states. Particles whose labels are given by the same as those of our in and out states, but these are particles which do not interact among each other. Now, if there were really no interaction between the particles, then the labels for the particles would definitely not change, and S beta alpha would be reduced to a Dirac delta symbol, delta beta minus alpha. Of course, here when I say Dirac delta symbol, delta beta minus alpha, we must remember that beta and alpha have labels for particles which can be continuous as well as discrete. So, delta beta minus alpha is really a product of a bunch of Kronecker delta symbols for the discrete indices and Dirac delta functions for the continuous parameters. Now, because of the interaction, S beta alpha actually differs from delta beta minus alpha, and the difference is actually expressible in terms of the matrix elements of the Lippmann-Schwinger matrix. And we had already seen earlier that this is the form that S beta alpha takes. Note that this is the part which has all the non-trivial interactions embedded in it. Finally, we have also shown that the S matrix, being a matrix which transforms a complete orthonormal set of states, the in states, into another complete orthonormal set of states, the out states, must be a unitary operator, and that is embodied in these two equations. Another result that we will need in the following is an expression for the in and out states psi plus minus alpha in terms of the corresponding free particle states phi alpha. Remember, psi alpha plus minus and phi alpha have the same particle labels, except that phi alpha is of course for the non-interacting case, and psi alpha plus minus will reveal these particle labels only if the measurements were done either in the remote past, as is the case for psi alpha plus, or in the remote future for psi alpha minus. And the way in which you get psi alpha plus minus connected to phi alpha is through these operators called Euler operators, omega at minus or plus infinity, where omega is an operator which you create out of the Hamiltonian h and the corresponding free Hamiltonian h0. Omega tau is e to the I h tau times e to the minus I h0 tau. And if I were to take these expressions for psi alpha plus minus and plug them in my expression for S beta alpha, that is the overlap between psi beta minus and psi alpha plus, what I am going to get is psi beta minus is of course omega plus infinity acting on phi beta, and psi alpha plus is omega minus infinity acting on phi alpha. And therefore, it is actually the overlap between these two states, phi beta and this, where I have actually moved the omega plus infinity from the left hand part of the inner product to the right hand part. Of course, it becomes its adjoint in the process. But we already know that S beta alpha is the overlap between phi beta and S acting on phi alpha. And this helps us to identify our S operator as this combination, omega dagger infinity times omega minus infinity. Something which we also call U with labels plus infinity and minus infinity, where U of tau and tau 0 is simply omega dagger tau, omega tau 0. That's why when you put plus infinity here for tau and minus infinity for tau 0, you actually get S. And if you just take the expressions that we had written down earlier for omega and plug that in here, what you will get is the expression e to the I h0 tau times e to the minus I h tau minus tau 0 times e to the power minus I h0 tau 0. This is the expression for u tau comma tau 0. If you take the limit of this expression, and there you have to be a bit careful because the limit may not always exist if you were to just do it in a brute force manner. But if you were to take the limit with tau going to plus infinity and tau 0 going to minus infinity, you will get the corresponding S matrix. Now this was a recap of whatever we have studied earlier. In the rest of this lecture, we are going to focus on the important symmetry properties which the S matrix elements have. In particular, in today's lecture, we are going to focus on the continuous Poincare transformations and the symmetries corresponding to that. Let me remind you that the Poincare transformation is one in which space-time coordinates x changes over to x prime, which is given by lambda x plus a, or in terms of coordinates, x prime mu is given by lambda mu nu, x mu plus a mu. Under such a transformation, the states of a quantum system transform by the action of a unitary operator acting on the states. And the basic idea here is that we can define a unitary operator u plus lambda a which acts on the in states and furnishes a representation of the Poincare group, and another of unitary operator u minus lambda a, which acts on the out states. On top of this, we should also have u0 lambda a, operators which furnish a representation of the Poincare group while acting on states of the corresponding free particles, non-interacting particles. So, from the theory that we have studied extensively in previous lectures, we know that when either of u plus or u minus lambda a act on psi plus minus with these particle labels p1 sigma 1 n1, p2 sigma 2 n2 and so on, the result is a linear superposition of lots of states. The p's all change to lambda p's, so p1 becomes lambda p1, p2 becomes lambda p2 and so on. The translation A causes this phase factor to come in to the minus ia mu times lambda p1's muth component plus lambda p2's muth component and so on. These are normalization factors which keep the normalization right. But more interestingly, there are these factors which are basically stating that different spin or helicity components get mixed together when you carry out a Lorentz transformation. Now, this is something which we have treated in quite some detail earlier. The important point is u plus acting on psi plus will produce a transformation law like this. U minus acting on psi minus will also produce a very similar, in fact identical looking transformation rule, because the structure of this transformation rule is essentially guaranteed by the algebra of the Poincare group itself. Now, the mere existence of a set of operators u plus lambda a or u minus lambda a, which act on the states in this particular manner, is not a guarantee that the theory is Poincare invariant. The only thing this really signifies is that the interactions between particles is sufficiently short-ranged so that in the remote past or in the remote future, the particles essentially behave like free particles. In order that the theory be Poincare invariant, we must impose the condition that the operators u plus and the operators u minus, which act on the in and the out states, must be identical operators. This is our definition of what Poincare invariance means. U plus of lambda a must be equal to u minus of lambda a, which we can just call u of lambda a. By the way, there is another bunch of operators called u0 of lambda a, which would implement the same transformation on free particles, on the phi a's, which could very well be different from this set u of lambda a. If a theory is Poincare invariant, then the consequence it has on the S-matrix elements is actually rather far-reaching. Firstly, S beta alpha, which is the overlap between psi beta minus and psi alpha plus, is of course the same as the overlap between u lambda a psi beta minus and u lambda a psi alpha plus. Note that these two operators are operators which act on the in and the out states respectively. But right now we are assuming that our theory is Poincare invariant, so rather than say u plus and u minus, I am just using u, the same operator. Because u is unitary, unitarity guarantees that this has to be the same as S beta alpha. Now just writing down the action of u lambda a on psi beta minus and psi alpha plus and calculating this matrix element immediately gives us the following result. S beta alpha, here for alpha, the initial state I have used p1 sigma 1 n1, p2 sigma 2 n2 and so on. For the final state, beta, I have used prime variables. So p1 prime sigma 1 prime n1 prime p2 prime sigma 2 prime n2 prime etc. refer to the outgoing state, the state beta. Now, this is of course S beta alpha, the left hand side of this expression. The right hand side, after you use this action, but this time remember it's u lambda a for both psi plus and psi minus. and calculate the inner product properly, you end up with a rather lengthy and messy looking expression. But it's rather easy to understand. For example, these factors all come from the conjugate of the factors which arise because of the action of u lambda a on psi beta minus. Here are the factors which you get because u lambda a is acting on psi alpha plus. Of course, the normalization factors come in from both beta minus and alpha plus, and you have two bunches of matrix elements sitting here. The notation that I am using, I am of course following Weinberg here, is that primes denote final state variables, and the bars here, both the sigma 1 bar here and sigma 1 bar prime here, or sigma 2 bar prime and so on, they denote summation variables, the variables over which you are actually summing up, which shows that you have superpositions of all different helicity states in the result of the Poincare transformation. So you ultimately get a rather messy looking restriction which the S matrix elements have to obey. Despite the rather messy form of this expression, there are some conclusions that you can draw almost immediately. Remember, this has to be true for arbitrary translations A and arbitrary Lorentz transformations lambda. Now, the left hand side of course has no trace of A in it. So the right hand side also has to be A independent. The only trace of A, the translation on the right hand side, is in this P factor. Since the right hand side also has to be independent of A, the only way that is possible is that the exponent must vanish. So the S matrix must vanish unless the sum of all the outgoing 4 momenta minus the sum of all the incoming 4 momenta is 0. In other words, there will be no possibility of a transition from alpha to beta unless the total 4 momentum of the initial state is exactly equal to total 4 momentum of the final state. So Poincare invariance here imposes the conservation of energy momentum. Now we had already figured out that the S matrix elements imposes energy conservation. If you don't have an interaction, you have delta beta minus alpha. The presence of the interaction is given by this term, which has this delta E beta minus E alpha factor. So energy conservation is imposed automatically. That's basically because all theories that we have were theories with time-independent Hamiltonians and they are automatically time translation invariant. What Poincare invariance does on top of this is to force 4 momentum conservation, not just energy. All the other 3 components, the spatial component of 4 momentum, must also be conserved. And therefore, what you ultimately end up with is this term has not only a delta of E beta minus E alpha, which is an energy conserving delta function, you have 3 more delta function factors, one for each spatial component of the momentum, and rolling them all together you can write this as delta 4 P beta minus P alpha. So of course delta cube P beta minus P alpha, the delta function imposing conservation of spatial momentum, will be there as part of T beta alpha plus in a Poincare invariant theory. And what we can do is we write T beta alpha plus as delta cube P vector beta minus P vector alpha times M beta alpha. So we can write S beta alpha now in terms of the matrix elements M beta alpha, and this final form imposes energy momentum conservation explicitly. Now remember, the fact that the same operators U lambda A implement the Poincare transformation on the in and the out states is a consequence of our assumption of Poincare symmetry. In fact, it can even be taken to be our definition of what Poincare symmetry is. This actually leads to rather severe constraints on the Hamiltonian describing our theory. In the rest of the lecture, we are going to actually discuss what these constraints are. And in order to do so, it will be more convenient if we talk in terms of the scattering operator S. Of course, our S beta alphas, the scattering matrix elements, are matrix elements of the operator S in the free particle states phi beta and phi alpha. As we have said before, free particle states have implementations of the Poincare transformation, and the corresponding operators U0 lambda A may very well differ from U lambda A, but the transformation that U0 lambda A enacts on the state phi P1 sigma 1 N1 P2 sigma 2 N2 and so on the state phi alpha, the same labels as before, is exactly similar simply because this is a feature of the Poincare group itself. And as a consequence, you can easily see that our demand of the Poincare invariance actually also can be written down in this form. Phi beta S phi alpha overlap, our S beta alpha, has to be the same as U0 lambda A phi beta's overlap with S U0 lambda A phi alpha. Note that U0 lambda A acting on phi beta and phi alpha respectively will give us factors which are like these, and when you combine them together you actually get exactly the p factors in S beta alpha which you have in this expression. And therefore, ultimately, the invariance properties of the scattering matrix elements can be just embodied in this equation. Of course, U0 lambda A being a unitary operator can be taken to this side as its adjoint, which is of course its inverse as well, and you get the result that phi beta S phi alpha has to be the same as phi beta's overlap with this operator U0 inverse lambda A S U0 lambda A acting on phi alpha. And this must be valid no matter which free particle states you take. So this is valid for all alpha and beta. And an immediate consequence of this is the following. U0 inverse lambda A S U0 lambda A, this operator, has to be exactly the same as the operator S. In other words, the operators which implement the representation of the Poincare group on the free particle states must commute with the scattering operator S. Now this relation is valid for arbitrary values of lambda and A. However, our experience with treatment of Poincare algebra earlier must have taught us that the obvious next step would be to consider infinitesimal transformations. So consider a lambda which is very close to the identity and an A which is a tiny infinitesimal translation. In other words, we are going to consider a U0 with parameters identity plus omega and an epsilon for the translation. Epsilon is infinitesimally small. The elements of omega, which of course obey omega mu nu equals minus omega nu mu, as we have already seen before, must also be infinitesimal quantities. And we have already learned that you can write down the group elements for infinitesimal departures from the identity in the form shown here. It's the identity operator plus first order terms which depend on the quantities omega mu nu and epsilon mu, and the corresponding operators sitting here are nothing but our familiar Lorentz group generators and translation generators. Of course, for the free theory, which is why we have J0 mu nu here and P0 mu here. Now, the fact that U0 commutes with S actually tells us that J mu nu 0 and P0 mu commutes with S. So basically, our job would be trying to figure out how you can get operators J0 mu nu and P0 mu which commutes with S. If you think in terms of the individual pieces of the J0 and P0, this boils down to the fact that H0, the free particle Hamiltonian, has to commute with S. The free particle momentum operator P0 vector, three components of course, P01, P02, P03, all three commute with S. Free particle angular momentum operator, which are generators of the rotation part of the Lorentz transformation, commutes with S. And the generators of the boost K0 also commutes with S. So basically all 10 generators of Poincare transformations must commute with S. Here we are talking about generators which generate Poincare transformations on free particle states. They must commute with a scattering operator. Now, the fact that H0, P0, J0 and K0 generate infinitesimal Poincare transformations on free particle states immediately tells us that they must satisfy a bunch of commutation relations. This Lorentz here should really be Poincare, but very often we will sort of interchange the two terms. Anyway, the commutation relations which these 10 operators obey among themselves should be very familiar. These, of course, are the standard angular momentum commutation relations which are valid even in non-relativistic quantum mechanics. This one and this one essentially just say that the boost operators and the momentum operators form a vector. These are additional commutation relations which we had figured out when discussing the algebra for the Poincare group. So what we need to do is formulate conditions on the interacting theory so that these 10 generators of the Poincare transformations acting on free particle states end up commuting with the S operator. Of course, just like these 10 operators which generate Poincare transformations on free particle states, we also have so-called exact generators. Momentum P, angular momentum J, boost generators K, which along with the full Hamiltonian H generate transformations induced by U lambda on the in states. In a Lorentz invariant theory, the same generators should generate transformations on the out states as well. And these generators also obey exactly the same commutation relations as do the free particle generators. Let me remind you once again that these commutation relations are basically a property of the geometry of the Poincare transformations. So these are completely independent of what states these operators are acting upon. Now, in virtually all known field theories, the exact generators P and J match the free particle generators P0 and J0. H, of course, is not the same as H0. We write H as H0 plus an interaction term which we are calling V. The V here might remind you of the potential energy term in non-relativistic quantum mechanics, but here V simply stands for the difference between H and H0. It's not really a potential energy. In a relativistic context, potential energy is not really that sensible a thing to talk about. Now, an immediate consequence of the fact that H and P commute, this is a part of the Poincare algebra, is that H0 plus V must commute with P0. Remember, P0 is identical to P. And since H0 commutes with P0, this immediately tells us that in a Poincare invariant theory, this extra piece, the interaction V, must commute with P0. And similarly, the fact that H commutes with J tells you that V has to commute with J0. So these are important restrictions on the interaction term in the Hamiltonian which Poincare invariance imposes. Of course, the first of these is simply a result of the fact that the theory has to be translation invariant, and the second is an embodiment of the fact that the theory has to be rotation invariant. Both translation invariance and rotation invariance are special cases of Poincare invariance, so these should not really come as a surprise. Indeed, these commutation relations guarantee that at least as far as translations and rotations are concerned, the in states and out states transform in exactly the same way as the free states do. In order to see this, let's take a look at the relationship between the in and out states and the free states. Remember, psi alpha plus minus is actually given by the molar operators omega at minus infinity and plus infinity, respectively, acting on the free particle state phi alpha. Omega tau is e to the IH tau times e to the minus IH0 tau. Now, rotation is imposed by an operator of this kind, e to the minus I theta dot j vector. It's easy to see that because j, which is the same as j0, commutes with both h and h0, e to the minus I theta dot j will commute with omega tau, and therefore with omega minus and plus infinity in general. And therefore e to the minus I theta dot j psi alpha plus minus will be equal to e to the minus I theta dot j acting on omega minus plus infinity phi alpha, and because of the commutation you can move the e to the minus I theta dot j to the other side, and therefore what you can see is if you first apply the rotation, j being the same as j0, this is exactly the same operator, on the free particle states, and then find the corresponding in and out states, the resulting thing is the same as first starting with the corresponding in and out state to the free particle state phi alpha and then rotating it. Of course, rotation of the free particle states, combine them together, e to the minus I theta dot j vector acting on phi alpha will be some specific combination C beta alpha of phi betas. But if you look at this really tells you that e to the minus I theta dot j acting on psi plus minus alpha is omega minus plus infinity acting on this linear combination C beta alpha phi beta, and therefore it will be equal to sum over all beta C beta alpha omega minus plus infinity acting on phi beta, that is psi beta plus minus. So under a rotation, the in and out states combine in exactly the same manner as the original free particle states do. Very similarly, the fact that e to the IA dot p, the operator which acts on a state when you carry out a spatial translation through a vector A, commutes with omega tau and hence with omega minus plus infinity in particular, and an immediate consequence is the way in which in and out states transform when you carry out a translation exactly mimics the way in which free particle states transform when you carry out the same translation. Now, the fact that P and J commute with both H and H0 makes it obvious that they commute with S. So that part of our job is done. But what about K? Can we use K equals K0? Which would of course have made this whole calculation rather trivial. However, that would be impossible because that would be inconsistent with our Poincare algebra itself. According to the Poincare algebra, the commutator of Ki and Pj is actually related directly to the Hamiltonian. And if we assume that K is the same as K0, given the fact that P is already the same as P0, K0i and P0j's commutator would have to be the same as Ki and Pj, and that would have implied that H0 is the same as H. In other words, there are no interactions whatsoever. Of course, a theory without interactions of a bunch of particles would definitely obey Poincare invariance. But that is a rather trivial case which we are not really interested in. We are interested in a case where H0 and H are different. In order to maintain that, we cannot have K0 the same as K. So the boost generators acting on in and out states must be different from the boost generators acting on the free particle states. So just like H becomes H0 plus V in the presence of interactions, K can be written down as K0 plus W. Of course, this is really saying nothing. It's just a definition of W at this stage. However, if you look at the commutator that K has with H, which is minus IP, remember P is the same as P0, so that's exactly the same as K0's commutator with H0. Now, if you write down K0 plus W instead of K and use the fact that K0 plus W's commutator with H has to be the same as K0's commutator with H0, this immediately gives you this particular expression. K0's commutator with H plus W's commutator with H minus K0's commutator with H0, which you have just taken to the other side, has to be equal to 0. And since H minus H0 is V, this gives us K0's commutator with V is minus W's commutator with H. So this gives us a relation which W, the change in the boost generator, must obey in order that the theory be Lorentz covariant. Now this may look like a big restriction for the operator W to satisfy, but frankly it's not really that big a deal. In order to figure out a W which satisfies this, all you have to do is give me the matrix elements of W with respect to some complete set of states. In particular, it is very easy to figure out what the matrix elements of W have to be with respect to the eigenstates of the Hamiltonian H. If you just take the matrix element of both sides of this expression with respect to exact eigenstates psi beta and psi alpha, by which I mean eigenstates of the exact Hamiltonian H, it's easy to see that from this side what you are going to get is a factor of E beta minus E alpha coming from the commutator with H acting on psi alpha in one term and on psi beta in the other. And then you can easily rewrite the matrix element of W between psi beta and psi alpha as minus psi beta's overlap with the commutator of K0 and V with psi alpha divided by E beta minus E alpha. So irrespective of whatever V we have, we can always find the W and hence a K for which at least this particular commutation relation, the commutation relation between K and H is satisfied. This, however, is not enough to have a Poincare invariant theory. In order to get a Poincare invariant theory, it is not enough to just find a set of Poincare generators that obey the correct algebra, although that of course is essential. What you also need is to ensure that they must act in the same manner on the in and the out states. Now this is the non-trivial part which we have to work on. Equivalently, we need to show that the free particle boost generator K0 commutes with the scattering operator S. We will show that provided an operator W, which has been defined like this, has certain nice smoothness properties, this will actually follow. So let us take a look at the proof of this now. We start with the fact that K0 commutes in a non-trivial way with H0, but in a rather simple way. The commutator of K0 and H0 is minus IP0. What we need to use next is something called the Baker-Hausdorff lemma, and it's basically a relationship which says that e to the lambda a b e to the minus lambda a, where a and b are operators, actually can be written in a rather simple infinite expansion, where the first term is just b, then the next term is lambda times commutator of a with b, the next term is lambda square by 2 factorial into a's commutator with the commutator of a with b, that is a double commutator. Of course, the third term will be lambda cubed by 3 factorial times a triple commutator, which we can write in shorthand as a comma b3, and it keeps on going like this. This is the standard Baker-Hausdorff lemma. Now, using the Baker-Hausdorff lemma, what we can do is figure out an expression for e to the minus IH0t K0 vector e to the IH0t. The first term is just K0 itself, the next term will be minus IT, the value of lambda, times the commutator of H0 with K0. The next term will be a double commutator and so on, but notice that H0's commutator with K0 is IP0 and that commutes with H0. So further higher order commutators, second, third and so on will all vanish. As a result, the infinite expansion that we have in the Baker-Hausdorff lemma simplifies a lot and you end up with just two terms, K0 from here and minus IT times plus IP0, therefore plus TP0 here. Now if I multiply through both sides by e to the IH0t, I can immediately rewrite this equation as K0 e to the IH0t is e to the IH0t K0 plus t times e to the IH0t P0. Of course, H0 commutes with P0, so I can write the e to the IH0t at the back. Therefore, what we see is that the commutator of K0 with e to the IH0t simply works out to be t times P0 e to the IH0t. Now, this is the result we are going to need in our proof that K0 commutes with S. In a very identical manner, you will also, of course, have the commutator of K with e to the IHT ending up as Tp e to the IHT, that is Tp0 e to the IHT. This is, of course, obvious because the result ultimately follows only from the Poincare algebra, and the generators for both the Poincare transformations on free states and the Poincare transformations on the in and out states ultimately obey the same algebra. Now, what we need to show is, of course, that K0 commutes with S. S, remember, is the limit as tau goes to plus infinity and tau 0 goes to minus infinity of the quantity u tau tau 0. So, this is the commutator that we are going to calculate next. The commutator of K0 with u tau tau 0. Let me remind you that u tau tau 0 can be written in terms of H0 and H simply in this fashion. And now, you can carry out the calculation of the commutator by breaking this up into three pieces. K0's commutator with e to the IH0 tau with the other two terms intact. Then e to the IH0 tau and e to the minus IH0 tau staying in their place. K0's commutator with this. And finally, K0's commutator with e to the minus IH0 tau 0. This is just a derivative property of a commutator bracket. That is, A commutator with BC behaves just like a derivative does. You get a commutator of A with B times C plus B times A commutator C. We have just used that to arrive at this. Using the fact that P and P0 both commute with H as well as H0, you can easily see that the terms here, the first, second and third terms, actually cancel each other out. So we are just left with this commutator. The first term on this commutator, of course, is minus e to the IH0 tau W times e to the minus IH tau minus tau 0 e to the minus IH0 tau 0. What we have done is I have just applied an extra e to the minus IH0 tau times e to the plus IH0 tau in the middle. Very similarly, if you look at the next term in the commutator, which will be e to the IH0 tau e to the minus IH tau minus tau 0, then you should have W e to the minus IH0 tau 0. I've just supplied the identity once again in between the two. The reason why I've done this is rather straightforward. This piece is, of course, nothing but u tau tau 0, and the same goes for this. So what we have is that our commutator of K0 with u tau tau 0 works out a minus W vector tau u tau tau 0 plus u tau tau 0 W vector tau 0, where W vector tau is simply defined to be the operator which we get when we carry out this particular symmetry transformation. Of course, this one is W vector tau and this one is W vector tau 0, which is what we have. Now, in order to achieve our objective of showing that K0 commutes with S, we need to show that this commutator vanishes in the limit when tau goes to plus infinity and tau 0 goes to minus infinity. Now, that's a slightly non-trivial result, so let me just work that out in a bit more detail here. What we need to inspect is basically what kind of matrix elements WT has when you sandwich them between eigenstates of H0, phi alpha and phi beta. Remember that in our actual physical system, we should consider superpositions of such free particle eigenstates, and that's what we are going to do next. But for the time being, as a step towards the calculation, let's calculate this particular inner product. This of course is the same as the inner product between phi alpha and e to the IH0t W e to the minus IH0t phi beta. E to the minus IH0t acting on phi beta obviously gives you e to the minus IE beta t times phi beta. But you can also simplify things a bit more beforehand by moving the e to the IH0t from here to the first factor in the inner product. Of course, what goes up here is the adjoint, namely e to the minus IH0t. And therefore, what you have is that e to the minus IE alpha t coming out from this and e to the minus IE beta t coming out from this factor. We can take both of these factors outside the inner product, and we have to remember that the inner product is linear in the second factor and antilinear in the first. So you will end up with e to the plus IE alpha t times e to the minus IE beta t times, of course, the inner product of phi alpha with W vector phi beta. This last inner product will be independent of the time t. Let us now try to figure out the matrix elements of this operator Wt between smooth superpositions phi g and phi h of these free particle eigenstates, where g alpha and h alpha are basically the weighting factors with which different energy eigenfunctions contribute. The calculation is pretty straightforward. You end up with an integral over alpha and beta of this inner product, and once again using the linearity properties of the inner product, what we end up with is this expression: d alpha d beta g alpha star h beta times the inner product of phi alpha with Wt phi beta, which we have just now worked out, and that gives us this expression ultimately. Note that this is the only time dependent term in the whole expression. Everything else is independent of the parameter t. Now comes a tricky statement, and that is the following: if the inner products phi alpha W phi beta are smooth enough as functions of E alpha and E beta, in particular, if they don't blow up when E alpha becomes equal to E beta, then it's easy to see that in the limit of t going to either plus infinity or t going to minus infinity, the rapid oscillations of these first factors will simply cancel out the integral, and we will end up with 0. So, this integral, which is a matrix element of Wt between any two smooth superpositions of the free particle eigenstates, must vanish in the limit tau going to plus minus infinity, provided of course that the matrix elements of k minus k0, that is W, do not have singularities like delta of Ea minus Eb in their expansion. So that is what we have to assume in order to show that our theory is Poincare invariant. Once we assume that our W is sufficiently smooth, the phase factor will be enough to make the inner products vanish in the relevant limits, t going to plus infinity and t going to minus infinity. And therefore, if you take that particular limit, what we will end up with is k0's commutator with u infinity minus infinity, that is k0's commutator with s, will vanish. If you come to think about it, the fact that Wt, that is e to the IH0t W e to the minus IH0t vanishes in the limit t goes to plus infinity and in the limit t goes to minus infinity is really not that surprising. Remember, the W is there in your theory primarily because there is an interaction, V. And if you were to form a similar operator V of t, e to the IH0t V e to the minus IH0t, matrix elements of this V of t, sandwiched between free particle states or superpositions of free particle states, would also have to vanish in the limit t goes to plus infinity or t goes to minus infinity. This is simply to ensure that once we go to the remote enough past or remote enough future, we can actually talk of particles as behaving like free particles. The whole concept of in and out states, and therefore the structure on which our scattering theory is based, depends on this fact. So, we have to assume that this kind of smoothness property of W actually exists, so that Wt vanishes in these limits. Now we have taken the limit as tau goes to plus infinity and tau 0 goes to minus infinity simultaneously in order to show that K0's commutator with S vanishes. We will be able to actually modify this argument slightly to show that K0 and K act in the same manner on free particle states and in and out states respectively. And for that, all you need to remember is the following. The commutator that we have is of course a commutator between K0 and U tau comma tau 0. And on the right hand side we have this W tau and W tau 0 appearing. Remember, U tau tau comma tau 0 is of course this, and omega tau, the operator which in the limit minus plus infinity gives us the in and the out states when acting on free particle states, is given by e to the IH tau e to the minus IH 0 tau 0. It is easy to see that if you put tau equal to 0 in U tau comma tau 0, it reduces to omega tau 0. So if we put tau equal to 0 and at the same time take tau 0 to the limits minus and plus infinity, U0 minus plus infinity actually becomes omega at minus plus infinity. So if you do that, then the commutator that we have between K0 and U tau comma tau 0 becomes the following. U tau comma tau 0 in the limit of course becomes omega minus plus infinity. On the right hand side, what we have is omega tau 0 which vanishes in the limit minus plus infinity. So this term goes away. But you also have W at 0. And W at 0 is obviously nothing but W itself. So you get W times U0 comma minus plus infinity. So minus W omega minus plus infinity. And if you expand out the commutator, it simply becomes this. And therefore, if you were to move the minus W from the right hand side here to the left hand side, what you will get is K0 plus W times omega minus plus infinity is omega minus plus infinity times K0. I have just taken this term to the other side. And therefore K omega minus plus infinity is omega minus plus infinity K0. Now this is exactly what you need to show, that the way in which K0 acts on the free particle states is exactly the same as the way in which K acts on the in. Before we go there, let me remind you that P and J actually obey exactly similar relations, and this is really rather trivial because both P and J commute with H and H0 and hence they commute with omega minus plus infinity. And it's really this commutation that is being stated here. I've just written P0 in place of P on the right hand side to emphasize the similarity with this equation and emphasize the fact that we are going to make these act on the free particle states, whereas these will act on the in and out states as the case may be. But otherwise, this is just a simple statement that the operator P and the operator J commutes with omega. We actually have a very similar relationship involving H and H0. And in order to see why this is true, all you have to do is see what happens when you apply this on a free particle energy eigenstate. So let's apply the whole thing on phi alpha. Of course, H0 acting on phi alpha will produce E alpha phi alpha, and E alpha being a number can simply be taken out of the whole expression. And therefore, what you will end up with is E alpha times omega minus plus infinity acting on phi alpha. So basically, the right hand side of this expression becomes E alpha times psi minus plus alpha. Psi plus minus alpha. What about the action of the left hand side on phi alpha? Well, if you were to apply omega minus plus infinity on phi alpha, this will give you psi plus minus alpha. And since psi plus minus alpha are H eigenstates, you will get the same result, that is E alpha psi alpha plus minus on the left as well. So these two operators give you exactly the same result acting on all free energy eigenstates. And since the free energy eigenstates form a complete basis, these two operators are one and the same. So we have a bunch of relations which essentially intertwine K, P, J, H with K0, P0, J0, H0 using the omega as the intertwiner, so to speak. Now we have seen what all of these equations mean right now when we talked about what this equation involving H and H0 did when you applied both sides to phi alpha. But just to see it in a slightly non-trivial context, what does this tell us about K's action on the in and out states? K acting on psi plus minus alpha must be K acting on omega minus plus infinity phi alpha. That's of course what psi plus minus alpha is. But because of the fact that if you were to interchange these two, K would change to K0 according to the relation we had just found out, we will get this. And what this relation tells us is that K0 acts on phi alpha to produce some combination of free particle states, and then omega acts on that to produce the same combination of the in and out states. So, whatever combination K0 acting on phi alpha produces, the same combination of in and out states is produced by K acting on psi plus minus alpha. We can of course make similar statements about the action of the other Poincare generators P, J and H, and as a result the in and out states do transform under the Poincare group like the free states. So we are nearly done. We have established that we do have operators which generate Poincare transformations on the in and out states in exactly the same manner as the free particle operators generate on the free particle states. Also, we have showed that the free particle Poincare group generators commute with the S operator, which will be essentially what we need to show Poincare invariance. Now you might have realized that we have not really shown that the new generators K, P, J, H actually obey all of the commutation relations for the Poincare group. However, we don't really need to do that. And the reason for that is simple. These relations that we have just found out, these four relations actually, can simply be rewritten to say that K, for example, is omega minus plus infinity, K0, omega dagger minus plus infinity. In other words, K is related to K0 through a similarity transformation. So is P, J and H related respectively to P0, J0, H0. And because of the similarity transformation, the commutation relations between K, P, J and H must be exactly the same as the commutation relations between K0, P0, J0 and H0. Hence, we don't really have to spend time proving that the other commutation relations are valid. Once we have established the fact that K, P, J, H acts in the same manner on the in and out states as K0, P0, J0, H0 does on the free particle states, we are actually through. In the coming lectures, we will have a lot more to say about the consequences of Poincare invariance on the S-matrix and in particular what kind of observational consequences this has. In the next part of this lecture, we are going to turn to the issue of internal symmetries, which are also of great importance as far as quantum field theories are concerned. So see you then. Bye for now.